Earth's gravity well is 63 million joules per kilogram deep. Every single kilogram you want to launch into space requires enough energy to power an average home for 6 days. Not to orbit, just to escape. And that's only the beginning of the problem. We dream of Mars colonies, interstellar travel, cosmic civilizations spanning galaxies. But the physics, biology, and economics of leaving Earth create barriers so fundamental, so insurmountable, that humanity may be permanently confined to this single planet. Not because we lack ambition, because reality has limitations we cannot engineer around. This is why we will never escape. For decades, we've been promised a spacefaring future. Moon bases by 2000, Mars colonies by 2030, interstellar probes by century's end. But despite spending hundreds of billions on space programs, fewer than 600 humans have reached orbit in 60 years. 0 have gone beyond the moon. 0 have established permanent off-world settlements. The obstacles aren't political or financial, they're existential. Physics, biology, and thermodynamics create walls that technology cannot breach. Tonight, we're examining why escaping Earth may be humanity's most impossible dream. Chapter 1. Gravity's Prison. Let's start with the most fundamental problem. Earth's gravity well. This isn't metaphor, it's precise physics. Gravity creates a potential energy barrier, a literal depth in space-time that requires enormous energy to escape. Every kilogram of mass at Earth's surface sits at the bottom of a well 63 million joules deep. To lift that kilogram to infinity, to truly escape Earth's gravitational influence, requires adding 63 megajoules of kinetic energy. That number should stagger you. 63 megajoules is roughly 17.5 kilowatt-hours of energy, enough to power an average American home for half a day for a single kilogram. A human body masses about 70 kilograms, requiring 4.4 billion joules, 1,025 kilowatt-hours, just for the body itself, before accounting for life support, spacecraft, fuel, or anything else. This is fundamental physics. You cannot negotiate with it or engineer around it. Escaping Earth's gravity requires this much energy, period. Now consider what it takes to actually provide this energy. Rockets work by Newton's third law. They expel mass in one direction to generate thrust in the opposite direction. The faster you expel this mass, the more efficient your rocket. This is quantified by specific impulse, measured in seconds, representing how long 1 kilogram of propellant can produce 1 kilogram force of thrust. Chemical rockets, the most powerful we have, achieve specific impulses around 450 seconds in vacuum. This sounds impressive until you calculate what it means. The rocket equation, derived by Konstantin Tsiolkovsky in 1897, governs all rocket propulsion. It states that delta V, change in velocity, equals exhaust velocity times the natural logarithm of initial mass divided by final mass. This logarithmic relationship is devastating. To achieve Earth escape velocity of 11.2 kilometers per second using chemical propellants with exhaust velocity around 4.4 kilometers per second requires a mass ratio of about 12.1, 12 kilograms of initial mass to deliver 1 kilogram to escape velocity. But it gets worse. That 12:1 ratio assumes you're already in space with no atmospheric drag, no gravity losses during ascent, no need for guidance systems or structural mass. Real rockets launching from Earth's surface must overcome atmospheric drag, fight gravity during the entire ascent, and include fuel tanks, engines, guidance computers, and structure. These factors typically triple or quadruple the required mass ratio. The Saturn V rocket that sent Apollo astronauts to the Moon had a fueled mass of 2,970 tons. The payload delivered to translunar injection was about 45 tons, a mass ratio of 66.1. Think about what this means practically. To send 1 kilogram to the Moon requires launching 66 kilograms from Earth's surface. To send a 70-kilogram human plus 200 kilograms of spacecraft and supplies requires launching 17,120 kilograms. To send 100 people, barely a village, requires launching 1.78 million kilograms or 1,180 tons. The entire International Space Station, humanity's most expensive construction project at over 150 billion, masses just 420 tons and houses 6 people. Earth's gravity, well, doesn't just make space travel difficult, it makes large-scale space colonization energetically prohibitive. Every kilogram of equipment, every solar panel, every pressurized module, every water recycler, every seed for growing food must be lifted out of this well at enormous energy cost. You cannot build a self-sustaining Mars colony by shipping materials from Earth because the energy cost of shipping exceeds Earth's total energy production capacity for anything beyond trivial scales. Some argue we could mine asteroids or the moon for materials, building in space from space resources. This sounds reasonable until you examine what it requires. Mining equipment must first be shipped from Earth. Thousands of tons of drills, crushers, refineries, manufacturing facilities, power generation systems. These systems must operate autonomously or with minimal human supervision in radiation-intense vacuum environments with no infrastructure support. Every failure requires shipping replacement parts from Earth. Every repair requires tools and materials brought from Earth. The energy economics are brutal. Suppose you want to mine an asteroid and return valuable metals to Earth. The asteroid is in the main belt, requiring delta V of roughly 10-12 kilometers per second for the round trip. Using current propulsion technology, this means mass ratios of 100.1 or higher, launching 100 kilograms to return 1 kilogram of material. Even if that kilogram is pure platinum worth $30,000, you've spent millions in launch costs to retrieve it. The economics never close unless asteroid materials stay in space for space construction, but that requires space infrastructure that doesn't exist and cannot be built without first shipping materials from Earth. Consider Mars, the most commonly proposed colonization target. Mars is less massive than Earth with lower surface gravity, just 38% of Earth's. But Mars has no magnetic field, a thin atmosphere providing no radiation shielding, surface temperatures averaging -60 Celsius, and no liquid water. Building a viable colony requires shipping not just people, but entire industrial civilizations worth of equipment, power generation, life support, agriculture, manufacturing, medical facilities, computing infrastructure, communication systems. NASA estimates a Mars mission for 4 astronauts staying 500 days would require launching 500-800 tons to Mars transfer orbit. This is for 4 people doing science experiments, not building a self-sustaining colony. A colony of 1,000 people, a small town, would require launching tens of thousands of tons. At current launch costs of roughly $5,000 per kilogram to low Earth orbit, this represents trillions of dollars. SpaceX's Starship aims to reduce launch costs to perhaps $100 per kilogram, but even at that optimistic figure, launching 50,000 tons costs $5 billion for one-time delivery, not including the cost of building what you're launching. And this assumes Mars colonization is possible at all, which requires solving problems we'll explore in depth. Long-term radiation exposure, biological adaptation to low gravity, psychological tolerance of isolation and confinement, ability to manufacture replacement parts for complex systems without Earth's industrial base. Every one of these represents a potentially insurmountable barrier, but they all rest on the foundation of Earth's gravity well, the first and most fundamental obstacle to space colonization. Gravity wells are deeper and more expensive to escape the more massive the planet. Earth sits in an unfortunate middle ground, massive enough that escaping requires enormous energy, but not so massive that technological species couldn't evolve. If Earth were twice as massive, escape velocity would be 15.8 kilometers per second, and chemical rockets couldn't achieve orbit at all. We'd be permanently trapped. If Earth were half as massive, space access would be far easier. We happen to exist on a planet where space travel is barely possible with chemical rockets, just difficult and expensive enough to prevent large-scale colonization. Some propose alternative launch methods to bypass rockets: space elevators, orbital rings, electromagnetic launchers. Each has fatal problems. Space elevators require materials with tensile strength exceeding anything that exists or can be manufactured. Carbon nanotubes in theory work, but manufacturing 36,000-kilometer cables with zero defects is impossible with current or foreseeable technology. Orbital rings require building massive infrastructure in orbit first, which requires launching it with rockets. Electromagnetic launchers subject payloads to accelerations that would destroy humans and most equipment. We are trapped at the bottom of a gravity well 63 million joules deep, using propulsion technology that converts chemical energy to kinetic energy at roughly 60% efficiency, requiring mass ratios of 50.1 or higher to escape, with energy costs that make large-scale space colonization economically impossible with any plausible technology, and gravity is just the first barrier. Chapter 2: Exponential Tyranny. The rocket equation isn't just an engineering challenge, it's a mathematical tyrant that makes most space missions physically impossible regardless of budget or technology. Understanding why requires examining the exponential relationship between payload and propellant that dominates all rocket-based transportation. Tsiolkovsky's rocket equation, dv Tsiolkovsky L m0 mf. Delta V is the velocity change you want to achieve. V is exhaust velocity of your propellant. m0 is initial mass including propellant. mf is final mass after propellant is expended. The natural logarithm relationship means that achieving higher velocities requires exponentially more propellant. Let's make this concrete. Suppose you want to send a 1-ton spacecraft to Mars. From low Earth orbit, this requires approximately 6 kilometers per second of delta V to enter Mars transfer orbit. Using hydrogen-oxygen rockets with exhaust velocity of 4.4 kilometers per second, the rocket equation gives 6 equal 4.4 x ln m0 over 1000. Solving, ln m0 over 1000 at 1.36, so m0 over 1000 over 3.9, meaning m0 over 3 to 900 kilograms. You need 900 kilograms of propellant to send 1000 kilograms to Mars. That seems manageable. But now suppose you want to land on Mars, explore and return. Landing on Mars requires another 6 km/s. Launching from Mars requires 4 km/s. Returning to Earth requires 4 km/s. Total mission, delta V, 20 km/s. This is where the tyranny becomes clear. If you need 20 km/s total, and you're using 4.4 km/s exhaust velocity, the rocket equation gives 20 or 4.4 x ln equal 1000, so ln m 1000, or 4.55, meaning m or 1000 or 94.6. Your initial mass must be 94,600 kilograms to deliver 1000 kilograms through the complete mission. You need 93.6 tons of propellant for 1 ton of payload. But wait, that propellant must itself be accelerated, which requires more propellant, which requires even more propellant in earlier stages. This is staging, breaking the rocket into sections that are discarded as they empty. Staging improves efficiency but introduces complexity. Each stage needs engines, structure, tankage, separation systems. These add dry mass that must be accelerated but provides no thrust. Typical rocket stages have structural coefficients around 10 to 15%, meaning dry mass is 10 and 15% of propellant mass. For our Mars mission needing 93.6 tons of propellant, structural mass might be 10 tons, bringing total mass to 104.6 tons. But this structural mass must also be accelerated, requiring additional propellant, which requires additional structure, in a recursive calculation that quickly spirals. Final mass ratios often exceed 100.1 for missions with high delta V requirements. The Apollo program demonstrated this perfectly. The Saturn V stack launching from Earth massed 2,970 tons. The command module returning to Earth massed 5.5 tons. Mass ratio 5:40.1. To send 3 astronauts to the Moon and back required launching 540 times their spacecraft's return mass. Scaling this to send 100 people would require launching 54,000 tons, essentially launching a fleet of 18 Saturn Vs. Now consider interstellar travel. The nearest star, Proxima Centauri, is 4.24 light-years away. At 10% light speed, a blazingly fast 30,000 kilometers per second, the journey takes 42 years. Reaching 10% light speed requires delta V of 30,000 kilometers. Using hydrogen-oxygen rockets with 4.4 km/s exhaust velocity, 30,000, 4.4x ln m0mf, giving ln m0mf equals 6,018. This means m0mf equals 6818, which is approximately 10 to the 2,961. Read that again. 10 to the power of 2,961. To send 1 kilogram to Proxima Centauri at 10% light speed using chemical rockets requires initial mass greater than 10 to the 2,961 kilograms. The observable universe contains about 10 to 53 kilograms of matter. You need more mass than exists in 10 to 908 observable universes. Chemical rockets make interstellar travel not just difficult, but mathematically impossible. Perhaps nuclear propulsion offers escape from this tyranny. Nuclear rockets achieve exhaust velocities around 9 km/s. Double chemical rockets for our interstellar mission, 30,000 or 9x ln mf. So ln m0mf 333, meaning m e333 or 10 Still impossible. You'd need more mass than 10,394 observable universes. Ion drives offer even higher exhaust velocities, 30 to 50 km/s, but microscopic thrust. Using 50 km/s exhaust velocity, 30,000, CY is 50x ln m0mf, giving m0mf around E600, even 10.260. Better, but still requiring more mass than exists in 10.207 universes. The rocket equation doesn't care about your technology. For high enough delta V, all rocket propulsion becomes impossible. What about nuclear fusion, you might ask? Fusion reactions convert about 0.7% of mass to energy, achievable with deuterium-tritium fusion. This sounds promising. Direct mass-energy conversion should overcome the rocket equation's exponential tyranny, but fusion rockets still obey conservation of momentum. The exhaust velocity is limited by the thermal velocity of fusion products, which for DT fusion is about 3 to 4% the speed of light, roughly 10,000 km/s. Using 10,000 km/s exhaust velocity for our interstellar mission, 30,000 to 10,000x ln m0mf, giving m0mf a 3 Finally, a feasible mass ratio. But there's a devastating catch: fusion rockets don't exist. Despite decades of research and hundreds of billions of dollars spent on fusion energy, we have never achieved sustained fusion reaction that produces more energy than it consumes. Fusion power remains perpetually 30 years away, and fusion propulsion requires not just breaking even, but achieving enormous power density in a lightweight space-qualified system. Even if fusion propulsion worked perfectly, 10% light speed enables only interstellar missions to the nearest handful of stars over multi-generational timescales. The Milky Way galaxy is 100,000 light-years across. Reaching the galactic center at 10% light speed takes 1 million years. Most stars are thousands or tens of thousands of light-years away. Humanity's entire written history spans only 5,000 years. Multi-million-year journeys exceed the timescale of human civilization itself. What about antimatter? Matter-antimatter annihilation converts 100% of mass to energy, theoretically enabling exhaust velocities approaching light speed. If we could achieve 50% light speed exhaust velocity, 30,000, 150,000 x ln m0mf, giving m0mf and 1.32. Your spacecraft could be mostly payload with minimal propellant. Except Antimatter doesn't exist naturally in significant quantities. It must be manufactured in particle accelerators at enormous energy cost. Current production rates are about 10 nanograms per year at facilities like CERN, requiring billions of dollars of infrastructure. A kilogram of antimatter would take 100 billion years to produce at current rates. And storing antimatter is nearly impossible. It annihilates on contact with ordinary matter, requiring magnetic suspension in perfect vacuum, with any containment failure causing catastrophic explosion. Every proposed solution to the rocket equation hits fundamental physical barriers: chemical rockets, proven technology, impossible mass ratios for interesting missions, nuclear fission, regulatory and engineering nightmares, modest improvement. Nuclear fusion doesn't exist as technology, still faces mass ratio problems. Antimatter can't be produced or stored in meaningful quantities. Some propose non-rocket propulsion, solar sails, laser propulsion, Bussard ramjets. Solar sails work for lightweight probes but provide minuscule acceleration, millimeters per second squared, requiring decades to reach interplanetary speeds. Laser propulsion requires megawatt laser arrays in space and kilometer-scale sails, infrastructure that doesn't exist. Bussard ramjets, which would collect interstellar hydrogen for fusion, face insurmountable engineering problems, including the need for magnetic scoops thousands of kilometers across. The rocket equation represents a fundamental constraint on transportation when you must carry your propellant with you. Escaping this constraint requires either external propulsion, which doesn't exist at scale, or propulsion that doesn't expel mass, which violates conservation of momentum. We are trapped by mathematics as much as by physics. And even if we somehow solved propulsion, if fusion drives or antimatter rockets or some unimagined technology made space travel energetically feasible, we'd immediately confront the next barrier: energy availability. Because even with perfect propulsion efficiency, moving mass requires energy, and the energy requirements for space colonization exceed human civilization's total energy production by orders of magnitude. Chapter 3. Energy. Walls. Energy is the currency of capability. Everything you do, moving, thinking, building, surviving, requires energy input. Space colonization requires energy on scales that dwarf human civilization's current production capacity, and achieving those scales faces fundamental thermodynamic limits. Human civilization currently uses about 580 exajoules per year, 5.8 kg 1020 joules. This comes primarily from fossil fuels, oil, natural gas, and coal. These are stored solar energy accumulated over millions of years that we're burning in centuries. They represent a one-time inheritance that's rapidly depleting. Proven reserves of oil will last perhaps 50 years at current consumption. Natural gas, 50 to 100 years. Coal, 150 years. After that, we need alternative sources. Renewable energy, solar, wind, hydro, is growing but still provides only about 15% of total energy. Solar and wind are intermittent, requiring storage systems that don't exist at necessary scale. Hydroelectric is geographically limited and mostly fully exploited. Nuclear fission could provide baseload power but faces political opposition, waste disposal challenges, and uranium supply limits. Nuclear fusion remains non-existent as practical technology. Now consider what space colonization requires. Launching 1 kilogram to low Earth orbit requires about 50 megajoules of energy. The International Space Station masses 420 tons, so launching it required 21 trillion joules, about 36 seconds of human civilization's total energy production. The ISS houses 6 people. A Mars colony of 10,000 people would require infrastructure massing perhaps 100,000 tons, requiring 5 hex 10^15 joules to launch, or about 24 hours of civilization's total energy output. But that's just to orbit. Actually sending that mass to Mars requires additional energy, For trans-Mars injection, landing it on Mars requires energy. Building habitats, life support, power systems, manufacturing facilities requires energy. Growing food requires energy. All told, establishing a 10,000-person Mars colony might require energy equivalent to several years of Earth's entire energy production, and that's before considering that the colony would need ongoing supply from Earth until becoming self-sufficient, which might never happen. Interstellar travel is worse by factors of billions. Consider sending a 1,000-ton generation ship to Proxima Centauri at 10% light speed. Kinetic energy equals 1/2 mass times velocity squared, e 0.5 x 10^6 kg x 3x 10 7/6 2 banged 4.5 x 10 ton 20 joules. That's approximately the total energy human civilization uses in 1 year, spent to accelerate a single ship. And you need that energy again to decelerate at arrival, doubling the requirement. Then again for return journey if round trip, quadrupling it. This assumes perfect efficiency, 100% conversion of energy to kinetic energy with no losses. Real propulsion systems have efficiency losses. Rockets waste energy, heating expelled propellant. Ion drives require power generation, conversion losses, and waste heat rejection. Even theoretically perfect photon rockets, if they could exist, would need 9 x 1020 joules to accelerate our ship, because photon momentum is EC, and achieving momentum MV requires energy, MC 2x VC to 2 for relativistic speeds. Where does this energy come from? Not from chemical fuels, they don't have sufficient energy density. Gasoline contains about 46 megajoules per kilogram. Our interstellar ship needs 4.5 k 10 times 20 joules, requiring about 10 trillion kilograms of gasoline, 10 billion tons or 10,000 times the ship's mass. This is the rocket equation again. Carrying fuel requires more fuel to accelerate the fuel. Nuclear fission of uranium-235 releases about 80 trillion joules per kilogram, almost 2 million times more energy dense than gasoline. To get 4.5 x 10 power 20 joules requires about 5,600 kilograms of uranium fully fissioned. But fission propulsion isn't 100% efficient. Thermal rockets convert maybe 40% of fission energy to kinetic energy. You'd need 14 tons of uranium, which starts multiplying through the rocket equation. Fusion would be better, but fusion propulsion doesn't exist. And even fusion has limits. Deuterium-tritium fusion converts about 0.7% of mass to energy, so getting 4.5 x 10^20 joules requires about 71 tons of fuel. Better than fission, but still substantial. And tritium is rare and radioactive with a 12-year half-life. Deuterium-deuterium fusion is much harder to achieve and releases less energy. Proton-proton fusion, what powers the sun, requires temperature and pressure conditions we cannot create artificially. Antimatter is the only fuel with sufficient energy density, 100% mass energy conversion. But as discussed, we can't produce or store it. Every technological path hits fundamental barriers. Even assuming we solve propulsion and launched ships, where does the energy come from on arrival? Mars receives about 590 watts per square meter of sunlight, 43% what Earth receives. Solar panels work, but you need vast arrays to power a colony. A 10,000-person colony might need 100 megawatts continuous power, 10 kilowatts per person, less than half what Americans use. At 20% solar panel efficiency and Mars sunlight, you need 850,000 square meters of solar panels, 850 hectares, or about 2,100 acres. That's over 3 square miles of solar panels on Mars. Manufactured where? Transported how? Nuclear reactors could provide power, but uranium is finite. Earth has maybe 8 million tons of reasonably extractable uranium. At current consumption rates, this lasts 200 years. Building colonies throughout the solar system would accelerate depletion. You can't run a multi-planet civilization on fission unless you solve breeder reactors, which we haven't, or find uranium deposits on other worlds. which may not exist in extractable concentrations. Fusion would solve the energy problem. Deuterium exists in vast quantities in ocean water. But fusion power has been 30 years away since the 1970s. Current fusion experiments like ITER consume more energy than they produce. Achieving net positive fusion is extraordinarily difficult. Achieving commercially viable fusion reactors that can be mass-produced and distributed throughout the solar system may be impossible. Consider the thermodynamic perspective. The second law of thermodynamics states entropy always increases in closed systems. Useful energy, energy available to do work, decreases over time as it converts to waste heat. Every energy conversion has losses. Rockets expel hot exhaust, wasting energy. Solar panels get hot, losing efficiency. Fusion reactors, if they worked, would produce enormous waste heat that must be radiated to space. Waste heat rejection is a critical constraint in space. On Earth, we dump waste heat into atmosphere and oceans. In space, the only heat rejection method is thermal radiation, which follows Stefan Boltzmann law. Radiated power equals emissivity times surface area times sigma times temperature to the fourth power. To reject megawatts of waste heat requires enormous radiator panels at high temperatures. A nuclear reactor producing 100 megawatts of power at 40% efficiency generates 150 megawatts of waste heat. Using radiators at 1000 Kelvin, hot enough to glow red, you need about 440 square meters of radiator per megawatt, so 66,000 square meters, 6 hectares of radiators. These must be deployed, maintained, protected from micrometeorites, and kept pointed away from the sun. Every power system requires massive infrastructure just for heat rejection. Energy density matters profoundly. Batteries store about 1 megajoule per kilogram. A Mars rover might need 100 kilowatt-hours for overnight operations, requiring 360 megajoules, meaning 360 kilograms of batteries per rover per night. Scaling this to colony operations requiring gigawatt-hours means millions of tons of batteries, which must be manufactured, transported, maintained, and eventually replaced. Human bodies are energy-consuming machines. An average person needs about 8-10 megajoules per day in food energy. 10,000 people need 100 gigajoules per day, or 36 terajoules per year. Growing food requires energy, lighting, if underground or in habitats, temperature control, water pumping, nutrient processing. On Mars, with limited sunlight and no natural ecosystem, the energy cost of food production could be double or triple the food's caloric content. Every industrial process requires energy. Manufacturing solar panels requires energy. Refining metals requires energy. Producing plastics and ceramics requires energy. Running computers and communications requires energy. Maintaining life support requires energy. A self-sustaining colony needs industrial capacity equivalent to a small country, all powered by energy sources that must function reliably for decades without Earth support. The energy wall isn't just about having enough total energy, it's about energy concentration, storage, conversion efficiency, and waste heat management. Chemical batteries are too low energy density for anything beyond small applications. Fossil fuels don't exist on other worlds. Nuclear fission requires finite fuel supplies. Fusion doesn't work. Solar power requires enormous infrastructure and doesn't work far from the sun. Antimatter can't be produced. We live on a planet where millions of years of stored solar energy, fossil fuels, enabled rapid industrialization and energy-intensive civilization. That's a one-time gift. No other planet offers equivalent free energy sources. Colonizing space means either bringing concentrated energy from Earth, limited by launch costs, or generating it locally from sources that are either low density, solar, non-existent, fusion, or finite, fission. Energy is the fundamental constraint on capability. Space colonization requires energy at scales beyond human civilization's current capacity, and achieving those scales hits thermodynamic limits that technology cannot overcome. Even if we solved the rocket equation somehow, we'd still need to solve where the energy comes from, how it's stored, how it's converted, and how waste heat is rejected, and none of these have solutions at the required scale. Chapter 4. Radiation. Death space is lethal, not metaphorically dangerous, literally lethal in multiple ways that make long-term human survival beyond Earth's protective magnetic field and atmosphere potentially impossible. Radiation exposure is the most fundamental and unsolvable of these threats. Earth's magnetic field and atmosphere protect us from ionizing radiation that would otherwise sterilize the planet's surface. Solar wind, charged particles streaming from the sun at hundreds of kilometers per second, would strip Earth's atmosphere away over millions of years if not deflected by our magnetosphere. Galactic cosmic rays, high-energy particles from supernovae and other energetic events throughout the galaxy, would deliver lethal radiation doses if not absorbed by our atmosphere. We evolved under this protection. Our biology assumes it exists. Remove it, and we die. Radiation comes in several forms, each damaging differently. Solar particle events, SPEs, occur when solar flares or coronal mass ejections accelerate protons and heavy ions to high energies. These particles travel at up to 90% light speed and arrive at Earth within hours or days of the solar event. On Earth's surface, we don't notice them. The atmosphere absorbs them. In space or on the Moon or Mars, they deliver potentially lethal doses. Galactic cosmic rays, GCRs, are far more energetic and harder to shield against. They consist mostly of protons but include heavy ions like iron nuclei traveling at 99% light speed with energies up to 10 to 20 electron volts. When these particles hit matter, they create cascade showers of secondary particles. Shielding that stops protons can actually make GCR exposure worse by creating more secondaries. You cannot effectively shield against GCRs with passive materials. Radiation damage occurs at the molecular level. High-energy particles passing through tissue ionize atoms, breaking chemical bonds and damaging DNA. Low doses cause minor damage that cellular repair mechanisms can fix. Higher doses overwhelm repair systems, causing mutations, cell death, and cancer. Very high acute doses, several sieverts delivered in hours, cause acute radiation syndrome, nausea, vomiting, organ failure, death within days to weeks. On Earth's surface, we receive about 2 to 3 millisieverts per year of background radiation from cosmic rays, radon, and naturally radioactive elements. This is considered safe. Our biology adapted to it. On the International Space Station, astronauts receive about 144 millisieverts per year, roughly 50 times higher. ISS is in low Earth orbit, still within Earth's magnetosphere, receiving partial protection. Beyond the magnetosphere, traveling to Mars or the Moon, exposure increases dramatically. A Mars mission lasting 900 days, 210 days travel each way, 500 days on surface, exposes astronauts to about 900 millisieverts, 0.9 sieverts. This exceeds career limits established for astronauts and significantly increases cancer risk. A 5% increase in lifetime fatal cancer risk is considered the threshold for unacceptable occupational exposure. A Mars mission likely exceeds this. Multiple missions over a career would be suicidal, but that's for short stays. Permanent colonization means lifetime exposure. Living on Mars without adequate shielding would expose colonists to roughly 200 millisieverts per year, approximately 100 times Earth's surface levels. Over a 50-year lifetime, that's 10 sieverts, enough to virtually guarantee fatal cancer and likely cause other radiation-induced diseases including cataracts, cardiovascular damage, and neurological degeneration. Build underground habitats, someone suggests. No, this helps. Regolith, Martian soil, provides shielding. 3 meters of regolith reduces radiation to near-Earth surface levels. But this requires excavation equipment, underground construction, life support in confined spaces. You can't farm underground without artificial lighting requiring enormous energy. You can't see the sky or feel sunlight. You exist in caves, dependent on technology for every breath and photon. And Mars is relatively close to Earth, inside the habitable zone, where solar intensity is substantial. Venture to the outer solar system, Jupiter's moons, Saturn's moons, asteroids, and solar intensity drops to percentages of Earth levels, while radiation from Jupiter's magnetosphere adds lethal doses. Europa, considered a potential habitat due to its subsurface ocean, orbits within Jupiter's radiation belts, receiving 5,400 millisieverts per day, a lethal dose in hours without massive shielding. Shielding mass scales linearly with protected volume but exponentially with required protection level. To reduce GCR exposure by 50% requires roughly 10 grams per square centimeter of aluminum, about 10 centimeters of solid aluminum. A small habitat 10 meters in diameter requires shielding mass of roughly 300 tons. Launching this from Earth at current costs, $5,000 key, costs $1.5 billion, just for the shielding of one small module housing maybe 6 people. Use water for shielding, others propose. Water effectively shields radiation and serves dual purpose as consumable and radiation barrier. But you need enormous quantities. A spacecraft designed with water-lined walls surrounding a 20 cubic meter habitat needs roughly 100 tons of water for adequate shielding. This water must be launched from Earth or obtained from ice deposits on other worlds, requiring mining infrastructure that doesn't exist. Active shielding using magnetic fields sounds promising. Generate an artificial magnetosphere around spacecraft or habitats. But the power requirements are staggering. Earth's magnetic field is generated by dynamo action in the molten iron core, essentially a planet-sized magnetic generator. Creating an artificial field strong enough to deflect GCRs requires superconducting magnets consuming megawatts of continuous power, adding weight for power systems, and creating electromagnetic interference with all electronics. Even with perfect shielding, radiation during transit remains problematic. A journey to Mars takes 6 to 9 months with current propulsion. Faster transit requires more energy, energy wall, or better propulsion, rocket equation. Generation ships to other stars would expose crews to decades or centuries of radiation exposure. Biological damage accumulates, mutation rates increase, cancer risk approaches certainty. Then there's solar particle events. These are unpredictable, sometimes weeks or months apart, sometimes several in a day. A large SPE can deliver 2,000 millisieverts in hours. On Earth, we're protected. On Mars, colonists would need storm shelters, small, heavily shielded chambers where they retreat during solar storms. But solar storms can last days. Staying in confined shelters interrupts colony operations. Miss a warning or shelter inadequately, and you receive potentially lethal doses. Biological effects extend beyond cancer. Radiation damages the central nervous system, causing cognitive impairment, memory loss, and behavioral changes. Studies of astronauts show measurable cognitive decline after just months in space. Long-term exposure could cause permanent neurological damage, colonists becoming progressively less capable of complex thinking, problem-solving, and maintenance of life-critical systems. Radiation affects reproduction. High doses cause sterility. Lower chronic doses increase mutation rates in germ cells, potentially affecting offspring. Children conceived and gestated in high radiation environments face unknown developmental risks. Studies are impossible. We can't ethically expose pregnant women to test radiation effects on fetal development. We literally don't know if human reproduction is viable in space environments, and we won't know without trying, which risks creating severely damaged or non-viable offspring. Consider multi-generational missions. A generation ship to another star might travel 100-200 years. Children born aboard would never have experienced Earth's protection. They'd develop under constant radiation exposure. Would they be viable? Would mutation accumulation over generations cause genetic degradation? Would populations become non-viable after several generations? These aren't hypothetical concerns. They're fundamental questions about biological feasibility that have no answers. The Moon offers no protection, no atmosphere, no magnetic field. Surface exposure is higher than deep space due to albedo neutrons created when GCRs hit the lunar surface. Lunar colonists must live underground or in heavily shielded habitats, facing the same constraints as Mars but with no atmosphere whatsoever for aerobraking or resource extraction. Asteroid habitats face identical problems plus micrometeorite impacts. Asteroids have no gravity to hold atmosphere, no magnetic fields, no protection whatsoever. Every habitat must be fully shielded pressure vessel, essentially a spacecraft that doesn't move. The engineering is monumentally difficult and expensive. Some propose rotating habitats, O'Neill cylinders or Stanford Torrey, providing artificial gravity through rotation, but these must still shield against radiation, requiring thousands of tons of shielding material. Where does it come from? If mined from asteroids, who mines it? With what equipment? Powered by what energy source? The infrastructure requirements cascade endlessly. Radiation-hardened electronics exist but are expensive, bulky, and less capable than standard electronics. Consumer electronics fail rapidly under radiation exposure. Computers, sensors, solar panels all degrade faster in space. A Mars colony's electronics would need constant replacement, requiring either ongoing supply from Earth, unsustainable, or local manufacturing capability, requires massive infrastructure. Perhaps genetic engineering could create radiation-resistant humans. Some organisms, tardigrades, certain bacteria, tolerate radiation far exceeding levels lethal to humans. But making humans radiation-resistant would require fundamental changes to DNA repair mechanisms, cell cycle regulation, and possibly metabolism. These changes might have unforeseen consequences. Cancer suppression mechanisms protect against radiation, but also prevent tissue regeneration. Alter them, and you might create humans who can't heal wounds. Even if we solved radiation for humans, what about food crops? Plants are radiation sensitive. Growing food in high radiation environments requires shielded greenhouses, more mass to launch, more infrastructure to build, more energy to power artificial lighting if shielding blocks sunlight. The complexity compounds. The fundamental problem is that life on Earth evolved under specific radiation conditions that don't exist elsewhere in the solar system. Removing that protection exposes biology to conditions it didn't evolve to tolerate. You can't adapt to 100 times normal radiation exposure through short-term acclimation. The damage accumulates faster than repair mechanisms can compensate. Radiation isn't the only lethal aspect of space, but it's among the most fundamental and hardest to solve. It requires either massive shielding, expensive, heavy, energy-intensive, to launch, or permanent underground habitation, psychologically challenging, agriculturally difficult, mining-dependent. Neither solution is satisfactory for large-scale colonization, and both require infrastructure and energy that create their own insurmountable barriers. Chapter 5. Distance Nightmare. The solar system is incomprehensibly vast, and interstellar distances are so large they reduce solar system scales to insignificance. This isn't poetic exaggeration. It's numerical reality that makes exploration and colonization practically impossible, even with optimistic technology assumptions. Earth to Moon, 384,000 kilometers. Light takes 1.3 seconds to traverse this distance. Apollo missions took 3 days. This is the only destination humans have reached beyond Earth orbit, and we haven't returned in over 50 years because the cost and risk remain prohibitive even for this relatively close target. Earth to Mars varies from 55 million to 400 million kilometers, depending on orbital positions. At closest approach, light takes 3 minutes. Spacecraft with current propulsion require 6 to 9 months. Communication latency at closest approach is 6 minutes round trip. Ask a question, wait 6 minutes for response. At farthest, 44 minutes round trip. Real-time communication is impossible. Remote operation of equipment requires autonomous systems that can function without immediate human oversight. This communication delay isn't just inconvenient, it's a fundamental barrier to effective problem solving. When problems arise, equipment failures, medical emergencies, unexpected discoveries, Mars colonists cannot consult Earth experts in real time. They must solve problems locally with available resources and knowledge. This requires complete self-sufficiency in technical expertise, medical care, engineering, manufacturing, essentially replicating Earth's entire knowledge base in a small colony. Earth to Jupiter, 588 million to 968 million kilometers. Light takes 33.54 minutes one way. Communication latency, 108 minutes round trip. Spacecraft with current propulsion require 1.52 years minimum. The Galileo mission, launched 1989, took 6 years to reach Jupiter using multiple gravity assists. Direct flight would be faster but requires more energy. Jupiter's moons, Europa, Ganymede, Callisto, are scientifically interesting but operationally nightmarish. Besides radiation, Europa receives lethal doses. The distance means any mission is essentially autonomous for hours at a time. Supply missions from Earth would take years. Equipment failures might mean waiting years for replacement parts. The logistics are barely conceivable. Earth to Saturn, 1.2 to 1.7 billion kilometers. Light takes 67.94 minutes one way. Cassini mission took 7 years to reach Saturn. Titan, Saturn's largest moon, has thick atmosphere and liquid methane lakes. Scientifically fascinating, but operating a human mission at Saturn, distances means colonists are fundamentally isolated. Help from Earth, if it comes, arrives years late. Earth to Uranus, 2.6 to 3.2 billion kilometers. Light takes 178 minutes one way, nearly 3 hours. Voyager 2 took 9 years to reach Uranus. Any mission to Uranus or beyond is essentially a one-way trip for current generation humans. By the time you arrive, decades have passed on Earth. Technology has advanced. Your mission design is obsolete. Returning means another decade in transit. Earth to Neptune, 4.3 to 4.7 billion kilometers. Light takes 4.5 hours one way. Voyager 2 took 12 years. At this distance, you're not part of human civilization in any meaningful sense. You're an isolated outpost where messages from home take 8 to 9 hours round trip, and physical travel takes decades. Pluto and the Kuiper Belt, 4.4 to 7.5 billion kilometers. New Horizons took 9.5 years to reach Pluto. Communication latency exceeds 9 hours round trip at closest approach. Beyond Pluto lie hundreds of Kuiper Belt objects, potential sources of volatiles and minerals, but reaching them requires decades of travel time with current propulsion. The Oort cloud, the distant shell of comets surrounding the solar system, extends from 2,000 to 100,000 AU, astronomical units. 1 AU equals Earth-Sun distance, about 150 million kilometers. The inner Oort cloud is 30 times farther than Pluto. Light takes 11 days to reach 2,000 AU. Spacecraft would require centuries. The outer Oort cloud at 100,000 AU is a quarter of the distance to Proxima Centauri. It's arguably where interstellar space begins. Now, scale up to interstellar. Proxima Centauri, the nearest star, is 4.24 light-years away, 268,000 AU or 40 trillion kilometers. At Voyager 1's current speed of 17 km/s, fastest human-made object, reaching Proxima would take 73,000 years. At 1% light speed, 3,000 km/s, requiring propulsion technology we don't have, the journey takes 424 years. At 10% light speed, 30,000 km/s, requiring truly speculative technology, 42 years. 42 years minimum for the nearest star. Most stars are hundreds or thousands of light years away. The Milky Way is 100,000 light years across. At 10% light speed, crossing the galaxy takes 1 million years, longer than humans have existed as a species. Intergalactic distances are millions to billions of light years. Andromeda Galaxy, our nearest large neighbor, is 2.5 million light years away, 25 million years at 10% light speed. These distances aren't just big numbers, they represent fundamental isolation. A colony at Proxima Centauri with 10% light speed travel capability is still 42 years from Earth. Send a message asking for help, and response arrives 8.5 years later. Send supplies, they arrive decades later. The colony must be completely self-sufficient for multiple generations before any help could possibly arrive. Multi-generational ships face psychological and biological challenges. Humans evolved as terrestrial beings on a planet with 1G gravity, breathable atmosphere, stable ecosystems. A generation ship is a closed ecosystem. Artificial gravity via rotation, recycled air and water, hydroponically grown food. Everything must function perfectly for decades or centuries. A single cascade failure could doom everyone. Population genetics requires minimum viable populations to avoid inbreeding depression. Estimates suggest 501,000 individuals minimum for long-term genetic viability. A generation ship carrying 1,000 people plus equipment, supplies and habitat mass would be enormous, tens of thousands of tons at least. Accelerating this to 10% light speed requires energy equivalent to decades of human civilization's total output. Energy wall again. Time dilation becomes significant at high speeds. At 10% light speed, time dilation is negligible. Ship time and Earth time are nearly equal. But at 90% light speed, if achievable, time dilation factor is 2.3. A 42-year journey to Proxima Centauri takes 18 years ship time. Sounds good, but Earth ages 42 years. Returning after exploration means arriving 84 years after departure. Everyone you knew is elderly or dead. You've become temporarily displaced from your own civilization. At 99.9% light speed, time dilation factor is 22.4. A 4.24-year journey takes 0.19 years ship time, 10 weeks subjectively. But Earth ages 4.24 years and the energy requirements are absurd. Relativistic mass increase means kinetic energy approaches infinity as velocity approaches light speed. Getting 1 kilogram to 99.9% light speed requires about 2x 10^17 joules, roughly 47 megatons of TNT equivalent. For a 1,000-ton ship, multiply by 1 million, 47 billion megatons, or energy equivalent to 900,000 years of human civilization's current energy output. Relativistic travel isn't just technologically difficult, it's energetically impossible at civilization scale. Even if we somehow achieved it for small probes, the time dilation creates causality problems. Send out generation ships at 0.1 C. Centuries later, develop 0.9 C technology. New ships launched later arrive first. The earlier colonists arrive to find their destination already inhabited by descendants of later missions. Social and political complications are staggering. Communication across interstellar distances creates fundamental isolation. Even with perfect radio equipment, messages are limited by light speed. A colony at Proxima Centauri exists 4.24 years in the past from Earth's reference frame. When they observe Earth, they see it as it was 424 years ago. When Earth observes them, we see them as they were 424 years ago. Real-time interaction is physically impossible. This isolation means each colony must maintain complete technological capability independently. If they need advanced electronics, they manufacture them locally. If they need medical expertise, they train it locally. If they need scientific knowledge, they generate it locally. Each colony must be a complete civilization, not an outpost dependent on home. The probability of success for interstellar colonization is extremely low given the distances, energies, and timescales involved. But even if one colony succeeded, it wouldn't constitute escaping Earth for humanity. One colony of 1,000 people doesn't preserve human civilization. It creates a tiny, isolated population that might survive or might fail. Earth remains home to billions, and those billions cannot evacuate to colony worlds light years away. Distance isn't just about travel time. It's about isolation, communication lag, self-sufficiency requirements, and energy costs that scale with distance and velocity. Every meter farther from Earth makes colonization exponentially harder. Mars is barely feasible, Jupiter's system is questionable, Saturn and beyond are practically impossible with foreseeable technology. Interstellar colonization is fantasy, not because we lack ambition, but because the distances are too vast, the energy requirements too high, and the isolation too complete. Chapter 6. Resource Trap. Every human activity requires resources, materials, energy, labor, time. Space colonization requires resources at scales that exceed Earth's ability to supply, creating a paradox. Colonies need Earth resources to become self-sufficient, but becoming self-sufficient requires infrastructure too massive to supply from Earth. Consider a minimal self-sustaining Mars colony. What would it need? First, life support. Systems to generate breathable atmosphere, recycle water, maintain temperature and pressure. These require equipment, pumps, filters, heat exchangers, pressure vessels, sensors, computers, redundant backups. Call it 10 tons of equipment per person, conservative estimate. For 10,000 people, 100,000 tons. Food production. Mars has no arable soil, no rain, no ecosystem. Everything must be grown hydroponically or in greenhouses using Martian regolith supplemented with nutrients. This requires greenhouse structures, transparent pressure vessels, growing systems, LED lighting, Mars sunlight is 43% Earth intensity, water recycling, nutrient synthesis, seed stocks. Estimate 20 tons of equipment per person for closed-loop food production, 200,000 tons total. Power generation, solar panels degraded by dust and radiation, or nuclear reactors. A colony needing 100 megawatts continuous power, 10 kilowatt per person, less than half US average, requires, at 20% solar efficiency under Mars sunlight, roughly 850,000 square meters of panels, at 5 kilowatt per square meter, including structure and wiring, 4,150 tons, or you need nuclear reactors, perhaps 10 megawatt reactors at 50 tons each, 500 tons, plus fuel, plus shielding, plus waste management. Manufacturing. To be self-sufficient, the colony must manufacture spare parts, tools, electronics, construction materials, replacement equipment. This requires metal refining from Martian ore, plastic synthesis from Martian materials, electronics fabrication, 3D printers requiring feedstock, machine shops, chemical synthesis facilities. Industrial equipment masses thousands of tons, for minimal capability, 50,000 tons. Transportation, rovers for surface exploration, cargo haulers, construction equipment, mining machinery, maintenance vehicles. Each vehicle masses tons. You need dozens to hundreds, 5,000 tons total. Medical, hospital facilities, surgical equipment, diagnostic tools, pharmaceuticals, lab equipment for synthesizing medicines locally. Estimate 1,000 tons. Construction, equipment to build habitats, excavate regolith for radiation shielding, manufacture building materials. Estimate 10,000 tons. Communications, equipment to maintain contact with Earth, internal colony communications, data storage. Estimate 500 tons. Total, roughly 400,000 tons of equipment and supplies to establish a minimally self-sufficient 10,000-person Mars colony. At launch costs of $100 kilograms, SpaceX's optimistic Starship target, this costs $40 billion just for launch. At the cost of manufacturing everything, likely $400 billion or more. Total, approximately $500 billion. more than the entire Apollo program adjusted for inflation, and Apollo sent 12 people to the moon for brief visits. But here's the trap, that 400,000 tons assumes the colony can become truly self-sufficient, manufacturing everything it needs from Martian resources. This assumption is wildly optimistic. Manufacturing complex electronics requires dozens of specialized materials. Microchips need ultra-pure silicon, rare earth elements for doping, complex lithography equipment. Where did these come from on Mars? Martian regolith contains iron, silicon, aluminum, magnesium, useful for construction. But extracting and refining them requires energy, equipment, expertise. You need mining equipment, manufactured where? Smelting furnaces, made of materials that withstand high temperatures, refineries, complex chemical processing, all operating in low pressure with temperature extremes, maintained by limited population with limited tools. Rare elements are particularly problematic. Modern technology requires copper for wiring, lithium for batteries, platinum group metals for catalysts, rare earths for magnets and electronics, chromium and nickel for stainless steel. Earth has concentrated ore deposits formed by billions of years of geological processes. Mars's geology is different. We don't know if economically extractable deposits exist. Mine asteroids, someone suggests. But asteroid mining requires spacecraft to reach asteroids, expensive, mining equipment, heavy, refining equipment, complex, transportation back to Mars or processing in situ. All this infrastructure must first be launched from Earth or manufactured on Mars from resources we're not sure exist in extractable form. The resource trap is this. You need infrastructure to achieve self-sufficiency, but building that infrastructure requires resources from Earth. But transporting resources from Earth is so expensive that achieving true self-sufficiency requires infrastructure mass you cannot afford to launch. Consider economic viability. A Mars colony must eventually pay for itself, either producing something valuable enough to export to Earth, covering cost of imports, or becoming completely self-sufficient, requiring no imports. What could Mars export? Raw materials. Shipping metals from Mars to Earth makes no sense. Mars' escape velocity is 5 km/s. Earth entry requires heat shielding, and metals are abundant on Earth. Launch costs exceed material value by orders of magnitude. Intellectual property? Mars colonists could develop patents, software, research. But why would research on Mars be more valuable than research on Earth, where you have vastly more resources, equipment, and researchers? Mars's only advantage is being on Mars, useful for Mars-specific studies, not for general scientific advancement. Tourism? At launch costs of $100 kg and human mass plus life support around 200 kilos per person, Mars tourism costs minimum $20 million per person, and that's just to get there. Return trip doubles it. Mars hotels, excursions, life support add more. Maybe billionaires would pay $50 million for Mars vacation, but this doesn't support colony of 10,000. You'd need thousands of tourists per year, which requires launch capacity that doesn't exist. The fundamental economic problem is that Mars has nothing Earth needs that's worth the cost of transportation. Earth has 8 billion people, vast infrastructure, concentrated resources, breathable atmosphere, comfortable gravity. Mars has rust-colored rocks, dust storms, lethal radiation, no atmosphere. Why go there except for scientific curiosity, which doesn't generate economic return? Some argue colonies provide backup for human extinction. If Earth suffers asteroid impact or nuclear war, Mars colony preserves humanity. But a Mars colony dependent on Earth for critical supplies dies when Earth dies. Only a truly self-sufficient colony survives, and achieving self-sufficiency requires resources we likely cannot afford to transport. Population dynamics worsen this. A colony of 10,000 people has limited genetic diversity, limited expertise, limited manufacturing capacity. Maintaining technological civilization requires vast supply chains. Your smartphone contains materials from dozens of countries, manufactured in specialized facilities, with equipment made in other facilities, all powered by global energy infrastructure. A Mars colony of 10,000 cannot replicate this complexity. Consider specialization. Earth's economy works through specialization. Farmers grow food, engineers design equipment, manufacturers produce goods, doctors treat illness, teachers educate children. Each person specializes, trading their specialized output for others' outputs. A Mars colony needs all these specializations but has tiny population. Each person must be versatile, but human lifespan limits expertise accumulation. You can't be expert farmer, engineer, doctor, and teacher simultaneously. Historical colonies on Earth had key advantages: breathable atmosphere, liquid water, existing ecosystems providing food, reasonable gravity, no radiation, communication with home. Even with these advantages, many colonies failed. Roanoke, various Arctic expeditions, isolated Pacific islands. Mars colonies face all these historical challenges, plus vacuum, radiation, toxic soil, transport lag, isolation measured in years, not months. Resource extraction on Earth took millennia to develop. Bronze Age began around 3300 BCE. Humans learned to extract copper and tin, alloy them into bronze. Iron Age began around 1200 BCE. Industrial Revolution, coal, steam power, advanced metallurgy started around 1760 CE. Modern electronics emerged mid-20th century. This technological progression took 5,000 plus years, built on accumulated knowledge, existing infrastructure, and abundant resources. A Mars colony must compress this into decades or become dependent on Earth forever. But compressing 5,000 years of technological development isn't achievable. It requires knowledge that took millennia to accumulate, infrastructure that took centuries to build, resources that took geological timescales to concentrate. The resource trap has no clear escape. Launching resources from Earth is too expensive. Mining resources on Mars requires equipment we must first launch from Earth. Manufacturing that equipment on Mars requires industrial base we must first launch from Earth. Each step requires the previous step's completion, but the first step, launching initial infrastructure, exceeds our economic capacity for scales necessary to achieve true self-sufficiency. You might achieve small scientific outposts, dozen people resupplied from Earth, conducting research like Antarctica bases, but self-sustaining colonies of thousands, cities of millions? These require resource inputs and industrial complexity that cannot be achieved within economic or physical constraints. And if Mars, the most accessible planet, with water ice, some atmosphere, 38% Earth gravity, faces insurmountable resource constraints, what hope for more distant destinations? Europa, Titan, asteroids, interstellar, each is harder, more distant, more resource-intensive. If we cannot escape Earth to Mars, we certainly cannot escape to Saturn's moons or neighboring stars. Chapter 7. Biological Fragility. Humans evolved for Earth. Every aspect of our biology, skeleton structure, cardiovascular system, immune response, circadian rhythms, reproduction, assumes specific conditions. 1G gravity, breathable atmosphere, adequate radiation shielding, diverse ecosystem. Remove these conditions and biology begins failing in ways we're only beginning to understand. Gravity is fundamental to human physiology. In microgravity, bones lose density at roughly 1% per month. Astronauts on 6-month ISS missions lose 6% bone density, equivalent to years of osteoporosis. Why? Bones maintain density through mechanical stress. Weight-bearing exercise signals bone-building cells, osteoblasts, to strengthen bone. Remove weight, remove signal, and bone-absorbing cells, osteoclasts, dominate. Bones weaken progressively. Muscles atrophy similarly. Without gravity to resist, muscles weaken. Astronauts lose up to 20% muscle mass in 6 months, despite rigorous exercise. Cardiac muscle weakens. The heart doesn't need to pump against gravity, so it atrophies. Blood volume decreases. Body adapts to not needing to pump blood upward from legs to brain. These adaptations make returning to gravity dangerous. Astronauts returning from ISS require weeks of rehabilitation. They're at high risk of fractures. Their bones can't handle normal weight. Their cardiovascular systems struggle. Standing causes blood to pool in legs, causing dizziness or fainting. Some effects may be permanent. Bone density doesn't fully recover. Now consider Mars, 38% Earth gravity. Better than microgravity, but sufficient? We don't know. No human has lived in reduced gravity long term. Does 0.38 g maintain bone density? Does it prevent muscle atrophy? Does it allow normal cardiovascular function? We have no data. It's possible humans adapt fine to Mars gravity. It's equally possible that 0.38 g is insufficient, causing slow degradation over years. Children are the critical unknown. Human development assumes 1 g. Bones grow under mechanical stress. Neural development requires sensory feedback from gravity. Cardiovascular development needs resistance to pump against. If children are born and raised in 0.38 g, do they develop normally? Do their bones achieve full density? Do their hearts develop adequate strength? We don't know. We can't know without experiments, and those experiments mean exposing children to potentially harmful conditions. Ethical science forbids experimenting on children with unknown risks. But without these experiments, we can't know if human reproduction and development is viable on Mars. Pregnancy itself raises questions. Does conception occur normally in reduced gravity? Does embryo implantation work? Does placental development proceed correctly? Does fetal development require 1 g mechanical stress? Birth in reduced gravity might be easier, less weight, or harder. Muscle contractions work differently. Post-birth, do infants develop normally? Do they reach developmental milestones on schedule? Every one of these questions has answers we don't have. The only way to get answers is to try, which means accepting unknown risks to pregnant women and fetuses. Few would volunteer for such experiments, and ethical review boards would likely refuse approval. Immune systems present another concern. Humans evolved with Earth's microbiome, trillions of bacteria, viruses, fungi, covering our skin, lining our digestive systems, inhabiting our environment. This microbiome is essential for health, gut bacteria, aid digestion, train immune systems, synthesize vitamins. In space's sterile environment, microbiomes change. Studies show astronaut immune systems become suppressed. Stress, radiation, altered microbiomes combine to reduce immune response. A Mars colony's closed environment would develop its own microbiome. Bacteria from humans, cultivated plants, equipment biofilms. But this microbiome would be impoverished compared to Earth's diversity. Would colonists develop immune deficiencies? Would opportunistic infections become common? Would lack of microbial diversity cause developmental problems in children? Circadian rhythms regulate sleep-wake cycles, hormone release, metabolism. Earth's 24-hour day synchronized our biology over millions of years. Mars's day is 24 hours 39 minutes, close to Earth's, but not identical. Do humans adapt to 24.65-hour cycles? Does the 39-minute difference accumulate sleep debt or circadian disruption? We don't know. ISS operates on 24-hour schedule despite not being on Earth, so we lack data on alternative day lengths. For moons of gas giants like Europa or Titan, day-night cycles are weeks or months long, tidally locked, one face always toward the planet. Do humans adapt to such cycles? Can artificial lighting maintain 24-hour rhythms? Probably, but long-term effects are unknown. Reproduction is evolution's ultimate test. If humans cannot successfully reproduce and raise healthy children off-world, colonies are temporary. They last one generation, then die out. Every biology concern, radiation, gravity, immune function, nutrition, affects reproduction. High radiation causes mutations in germ cells, eggs and sperm, potentially increasing birth defects or spontaneous abortions. Reduced gravity might affect fetal development, fluid distribution, organ positioning, skeletal formation, all assume 1G. Closed environments with limited genetic diversity increase inbreeding risk. Even with 1,000 colonists, genetic diversity is limited compared to Earth populations. Inbreeding depression over generations causes increased genetic disease, reduced fertility, lower intelligence. Nutrition in space colonies raises concerns. Hydroponically grown food lacks the mineral diversity of Earth-grown food cultivated in rich soil with diverse microorganisms. Mars soil contains perchlorates, toxic compounds that must be removed before use. Food variety on Mars would be limited. Growing staple crops is achievable, but growing the hundreds of plant species humans eat on Earth is impractical. Limited diet might cause subtle nutritional deficiencies affecting health and development over years. Vitamin D requires sunlight exposure or supplementation. On Mars, with lower sunlight intensity and colonists living in shielded habitats to avoid radiation, vitamin D deficiency is likely. Supplementation is possible, but requires importing vitamins from Earth or synthesizing them locally, adding to resource requirements. Mental health is biological as much as psychological. Depression, anxiety, and stress hormones affect brain chemistry, immune function, cardiovascular health. Space colonization involves isolation, confinement, danger, limited contact with Earth, all stressors known to cause mental health problems. Long-term stress causes elevated cortisol, which suppresses immune function, increases inflammation, accelerates aging. Sleep quality in space is poor. Astronauts average 6 hours per night versus 7 to 8 on Earth. Chronic sleep deprivation causes cognitive impairment, increased disease risk, shortened lifespan. A Mars colony where everyone is sleep deprived and stress elevated would suffer reduced productivity, more accidents, more illness, shorter lives. Sensory deprivation is another factor. Humans evolved with rich sensory environments, varied landscapes, sounds, smells, tastes. A Mars habitat is monotonous. Same walls, same filtered air, same recycled water, limited food variety. Monotony causes psychological stress and may have biological effects. Studies show enriched environments promote neuroplasticity, while impoverished environments cause cognitive decline. Aging might accelerate off-world. Radiation, stress, altered gravity, poor sleep, limited nutrition, each ages the body. Telomere shortening, cellular senescence, accumulated DNA damage all accelerate under stress. Mars colonists might age faster than Earth humans, experiencing age-related diseases decades earlier and shorter lifespans. Medical care on Mars faces severe limitations. Earth medicine relies on vast pharmaceutical industry, specialized equipment, trained specialists. A Mars colony would have limited medical supplies, limited diagnostic equipment, few doctors with limited specialties. Complex surgeries require specialized facilities. Cancer treatment requires chemotherapy drugs or radiation therapy equipment. Organ transplants require immunosuppressive drugs. None of this is feasible on Mars at small scales. A colonist developing cancer faces death. Treatment isn't available. Someone needing appendectomy might survive if colony has surgeon, but complications could be fatal. Heart disease, kidney failure, neurological conditions all become death sentences without Earth's medical infrastructure. Genetic diseases are particularly problematic. On Earth, genetic counseling and reproductive technologies help carriers avoid passing conditions to children. On Mars, with limited population, carriers might be a significant percentage of breeding population. Over generations, genetic diseases could become common, reducing colony viability. The fundamental problem is that human biology is adapted to Earth conditions and may not be adaptable to off-world conditions. Evolution requires generations to adapt, but adaptation requires surviving those generations, which requires biology that already works. We're trapped in a catch-22. Biology needs to adapt to survive off-world, but surviving long enough to adapt requires biology that's already adapted. Some propose genetic engineering, modify humans for space environments, make us radiation-resistant, low-gravity adapted, able to synthesize nutrients we normally get from diet. But such modifications are decades or centuries from feasible, require technologies we don't have, and raise profound ethical questions. Would modified humans still be human? Would they be viable on Earth if they return? Biological fragility isn't just about individual health, it's about species viability. Can humans reproduce and raise healthy children off-world? Can those children do the same? Can a population sustain itself biologically over generations? We don't know, and we can't know without trying. And trying risks creating populations doomed to genetic degradation, poor health, and eventual extinction. Chapter 8. Infrastructure. Impossibility. Modern civilization rests on infrastructure so complex, so interdependent, that most people never consider it. Water treatment plants, electrical grids, transportation networks, communication systems, supply chains spanning continents, all work seamlessly, usually, because they're maintained by millions of people with specialized expertise using equipment made by other specialists. A space colony must replicate this complexity with tiny population, limited resources, no supply chains, and hostile environment. The scale of this challenge borders on impossible. Consider water systems. On Earth, water treatment involves collection, reservoirs, aquifers, purification, filtration, chemical treatment, UV sterilization, distribution, pumps, pipes, pressure regulation, waste treatment, sewage processing, bacterial digestion, returned to environment. This infrastructure was built over decades, maintained by thousands of workers, supplied by global manufacturing base. A Mars colony needs closed-loop water recycling, every drop reused indefinitely. This requires collection of all wastewater, shower, sink, toilet, atmospheric condensation, filtration to remove solids, chemical treatment to eliminate contaminants, biological processing to break down organic compounds, distillation or reverse osmosis for final purification, constant monitoring for bacterial contamination, and storage with temperature control to prevent freezing or overheating. Each step requires equipment, filters, which clog and need replacement, pumps with mechanical parts that wear, sensors requiring calibration, chemical supplies needing replenishment or synthesis, and backup systems for when primary systems fail. On Earth, when a water treatment plant has problems, you call specialists who arrive with replacement parts manufactured elsewhere. On Mars, you manufacture the parts yourself or do without water. Equipment failure becomes life-threatening within days. Atmospheric systems are even more critical. Humans need oxygen at partial pressure of roughly 21 kilopascals, Earth's oxygen partial pressure at sea level. Too little causes hypoxia and death. Too much causes oxygen toxicity. Carbon dioxide must stay below 0.5 kilopascals. Higher levels cause hypercapnia, headaches, cognitive impairment, eventually death. Maintaining atmospheric composition requires oxygen generation, electrolysis of water or chemical oxygen generators, CO2 removal, chemical scrubbers using lithium hydroxide or molecular sieves, pressure regulation, airlocks, pressure sensors, automatic controls, humidity control. Too dry harms mucous membranes, too humid promotes mold, temperature regulation, heating, cooling systems, and trace contaminant removal, outgassing from plastics, human metabolic byproducts, equipment off-gassing. The ISS demonstrates this complexity. It has multiple redundant oxygen generation systems, CO2 scrubbers that need regular replacement, air circulation fans, temperature control systems, and constant monitoring. It costs roughly $3 to $4 billion per year to operate, supported by space agencies of multiple nations. A Mars colony must achieve similar reliability with far less support. Power infrastructure is foundational. Everything else requires electricity. Solar panels degrade from radiation and dust accumulation. Mars's frequent dust storms can block sunlight for weeks, requiring either massive battery storage, heavy, expensive, finite lifespan, or alternative power sources. Nuclear reactors require fuel, eventually depleted, cooling systems, difficult in vacuum or thin atmosphere, radiation shielding, massive, and maintenance by trained nuclear engineers. Electrical distribution requires wiring, circuit breakers, transformers, voltage regulation, all subject to failure. Short circuits, insulation breakdown, component failure, each requires repair capabilities. On Earth, you order replacement parts. On Mars, you manufacture them from local resources if possible, or jury-rig solutions with available materials. Communications infrastructure connects colony internally and to Earth. Internal communication requires computer networks, servers, routers, cables, or wireless systems, all requiring power and maintenance. Earth communication requires high-gain antennas, signal processing equipment, power amplifiers, and scheduling to account for Mars-Earth distance varying from 3 to 22 light-minutes delay. When Mars is on opposite side of Sun from Earth, solar conjunction, occurring roughly every 26 months, direct communication is impossible for weeks due to solar radiation interference. Colonies need communication satellites at Mars Lagrange points or elsewhere to maintain contact, adding infrastructure complexity and cost. Thermal control is surprisingly difficult. Space is an insulator. Vacuum doesn't conduct heat, so the only heat loss mechanism is radiation. Habitats must radiate waste heat to space using radiator panels while preventing heat loss from living spaces. This requires insulation, multi-layer insulation or regolith barriers, radiator surfaces, large area panels, heat pumps or fluid loops to transfer heat from habitats to radiators, and control systems managing temperature gradients. During Mars Day, solar heating might overheat habitats. At night, temperatures plunge to 80 degrees Celsius or lower. Managing these swings requires active thermal control, consuming energy continuously. Pressurization and structural integrity are life-critical. Habitat structures must maintain pressure difference of roughly 100 kilopascals, Earth sea level pressure, against Mars's 0.6 kilopascal atmosphere, essentially vacuum. Any crack, seal failure, or structural breach causes rapid depressurization, potentially fatal within minutes. This requires pressure vessel construction, thick-walled structures or inflatable habs with redundant layers, airlocks, complex mechanical systems with multiple seals, pressure monitoring, constant sensor surveillance, leak detection, sensitive enough to find small breaches, and repair capabilities, patching materials, welding equipment, skilled workers. Micrometeorites and dust storms threaten structures. Mars has no atmosphere thick enough to burn up micrometeorites. Regular impacts, though small, gradually degrade structures. Dust storms deposit charged dust that clings to everything, infiltrating seals and mechanisms. Preventing dust intrusion requires sophisticated airlock designs and constant maintenance. Transportation infrastructure enables colony expansion and resource utilization. Surface rovers require power systems, batteries or fuel cells, propulsion, electric motors, navigation, GPS equivalent, doesn't exist on Mars, requires local positioning system, environmental protection for electronics and mechanical parts, and maintenance facilities, repair shops, spare parts, trained mechanics. Each rover is complex machine requiring specialized manufacturing. Wheels wear on abrasive Martian regolith, metal wheels on Curiosity and Perseverance show significant damage after just kilometers of travel. Bearings need lubrication that doesn't evaporate in near vacuum. Electronics need radiation shielding and thermal protection. Manufacturing infrastructure enables self-sufficiency but requires enormous complexity. To manufacture even simple items like bolts or wiring requires raw material extraction, mining regolith, material processing, separating desired elements, refining, producing pure metals or compounds, fabrication, casting, machining, extrusion, and quality control, testing for defects. Advanced manufacturing, electronics, precision equipment, chemical products, requires even more infrastructure. Semiconductor fabrication needs ultra-clean rooms, photolithography equipment, chemical vapor deposition systems, molecular-level precision. These facilities cost billions on Earth with global supply chains. Replicating them on Mars with local resources is nearly impossible at colony scales. 3D printing helps but has severe limitations. Metal 3D printers can make structural parts but require feedstock, metal powder, manufactured from Martian ores. They can't make electronic components, can't manufacture complex assemblies with multiple materials, can't achieve the precision of traditional manufacturing for many applications. Medical infrastructure saves lives but requires vast resources. Basic medical care requires diagnostic equipment, X-ray, ultrasound, blood analyzers, surgical facilities, sterilization equipment, anesthesia, monitoring devices, pharmaceuticals, antibiotics, painkillers, anesthetics, vaccines, and trained personnel, doctors, nurses, surgeons, specialists. Advanced care requires even more. MRI or CT scanners, extremely heavy and power-intensive, dialysis machines for kidney failure, ventilators for respiratory failure, chemotherapy drugs for cancer, immunosuppressants for transplants, and specialists with years of training. A colony of 10,000 might have 10-20 doctors covering various specialties. What happens when someone needs cardiac surgery but you don't have cardiac surgeon? Or needs cancer treatment you can't provide? They die. Medical limitations mean reduced life expectancy and preventable deaths. Agricultural infrastructure grows food but requires controlled environment facilities, greenhouses or indoor farms, lighting systems if sunlight insufficient, irrigation, water distribution to plants, nutrient delivery, hydroponic or aquaponic systems, pollination, natural or manual. Mars has no insects. Pest control without ecosystem, pests that arrive might have no predators, and seed plant storage, genetic diversity for crops. Food production must be reliable. Crop failures cause famine. On Earth, crop failures in one region are compensated by imports from others. On Mars, crop failure means starvation unless you have massive stored reserves, requiring storage facilities, preservation systems, rotation schedules. Waste management closes loops but requires solid waste processing, separation, recycling, disposal, biological waste treatment, composting or incineration, hazardous waste handling, chemicals, radioactive materials, and materials recovery, extracting useful materials from waste streams. Every system requires redundancy, primary system plus backup, ideally plus second backup. Redundancy multiplies mass, complexity, and maintenance burden. It also means more systems that can fail, requiring more spare parts, more expertise, more resources. The interdependency problem is critical. Power systems need cooling, cooling needs power. Water systems need power and spare parts. Manufacturing spare parts needs water and power. Communications need power. Repairing power systems needs communication for coordination. Agriculture needs water and power. Maintaining water power systems needs food to feed workers. When one system fails, cascades can occur. ISS has experienced cascade failures where one problem triggers others. Coolant loop failure causing power system overheating, causing communications problems. On ISS, mission control helps troubleshoot and supply ships bring replacements. On Mars, you're on your own. Historical precedent is discouraging. Complex systems on Earth fail regularly despite enormous maintenance efforts. Power grid blackouts, water main breaks, sewage overflows, bridge collapses all occur in infrastructure built and maintained by millions of workers with unlimited resources. A Mars colony with a few thousand people, limited resources, and no supply chain would face higher failure rates and fewer options for repair. The fundamental problem is that infrastructure complexity scales with population size and technology level, but maintenance capability scales with population size and resource availability. A Mars colony needs Earth-level infrastructure complexity to maintain livable environment, but has tiny population and limited resources. The math doesn't work. You need 100,000 people maintaining infrastructure built for 10,000. Or you need infrastructure so simple it can be maintained by 100 people, but that simple infrastructure can't support 10,000 people. Infrastructure impossibility means that even if you solved every other problem, propulsion, energy, radiation, biology, you'd still face the challenge of building and maintaining complex systems without the industrial base and population that make such systems viable on Earth. Chapter 9: Psychological Cage. Humans are social animals who evolved in diverse, open environments with natural light, weather patterns, and complex ecosystems. We're psychologically adapted to Earth's conditions as much as biologically adapted. Removing these conditions creates psychological stresses that may be unsurmountable for long-term space habitation. Consider confinement. ISS astronauts live in a module roughly the size of a 6-bedroom house, shared by 6 people for 6 months. They report cabin fever, interpersonal tension, and profound psychological relief upon returning to Earth's open spaces. Antarctic research stations, among Earth's most isolated outposts, experience similar effects. Winter over crews of 50-100 people in stations offering more space than ISS habitats still report depression, interpersonal conflicts, and what's called winter over syndrome, psychological deterioration during months of isolation and darkness. A Mars colony would be far more confined. Radiation requires living underground or in heavily shielded structures. Surface excursions require spacesuits, bulky, restrictive, requiring constant life support monitoring. You can't go for a walk, feel wind on your face, or experience weather. You live in artificial spaces with recycled air, artificial lighting, and the same walls every day for years or decades. The psychological research is concerning. Isolation studies, where volunteers live in confined spaces for months, consistently show psychological degradation over time: depression, anxiety, irritability, cognitive impairment, and interpersonal conflicts. The longer the isolation, the worse the effects. Multi-year isolation hasn't been extensively studied because it's considered unethical, but extrapolating from shorter studies suggests severe problems. Social dynamics in small, isolated groups follow predictable patterns. Initially, people cooperate enthusiastically. The honeymoon period. After weeks or months, interpersonal tensions emerge. People develop grievances, factions form, conflicts escalate. In Antarctic stations, fights have occurred. On submarines, crew cohesion is maintained through rigorous training, clear hierarchy, and regular rotation back to port, none of which fully apply to permanent Mars colonies. A Mars colony of 10,000 sounds like a decent population, but it's actually tiny. Everyone would know everyone, or at least know of them. Privacy would be limited. Rumors would spread rapidly. Social conflicts would affect everyone. On Earth, if you dislike your neighbors or co-workers, you move elsewhere. On Mars, there is no elsewhere. You're trapped with the same people for life. Relationship problems become existential issues. Divorce, breakups, family conflicts all occur in confined space where you still encounter your ex daily. Dating pools are tiny. 10,000 people isn't much genetic diversity, and social, cultural factors further limit compatible partners. Some colonists might never find compatible partners, leading to loneliness and reduced reproductive fitness. Children raise special concerns. Human childhood requires exploration, play, social interaction with diverse peers, and gradual independence. Mars children would grow up in confined spaces, limited social circles, and constant danger requiring strict supervision. Could they develop healthy psychology under such constraints? Would they have childhood trauma from confinement, lack of nature, and awareness of living in hostile environment where any system failure means death? Teenagers are particularly concerning. Adolescence involves pushing boundaries, seeking independence, risk-taking. On Earth, this is challenging but manageable. On Mars, teenage rebellion could be fatal. Unauthorized surface excursions, tampering with life support, refusing to follow safety protocols could endanger entire colony. How do you give teenagers age-appropriate autonomy when the environment permits no margin for error? Cultural and intellectual impoverishment are inevitable. Earth offers vast cultural diversity, thousands of cultures, millions of artists and writers, billions of people creating content. A Mars colony of 10,000 has limited cultural production. You might have talented artists and musicians, but not orchestras, not film industries, not literary traditions. Cultural life would be impoverished compared to Earth. Education faces similar limits. On Earth, students can pursue virtually any field. Universities offer hundreds of majors, expertise in countless specializations. Mars colony education focuses on survival-relevant skills: engineering, agriculture, medicine, maintenance, philosophy, art history, literature. These might exist as hobbies, but not as career paths. Intellectual diversity would be severely limited. The communications lag with Earth creates isolation that's hard to overstate. A closest approach, 6-minute round-trip delay, makes conversation awkward. At farthest, 44-minute delays make real-time interaction impossible. You can't call family and have a conversation. You send messages and wait hours for responses. Relationships with people on Earth gradually fade. You drift apart because interaction is too difficult. Watching Earth media helps maintain connection, but also highlights what you're missing. Seeing forests, oceans, animals, cities, all reminding you that you're living in metal boxes on a frozen desert. This could increase depression and feelings of exile. The overview effect, the profound cognitive shift astronauts report when seeing Earth from space, initially seems positive, but long-term it might be psychologically damaging. Seeing Earth as a beautiful, fragile oasis makes Mars seem even more barren and hostile by comparison. The constant awareness that you're separated from humanity's home by millions of kilometers of lethal void could induce existential dread. Purpose and meaning become critical for psychological health. On Earth, people find meaning in diverse ways: careers, relationships, hobbies, religion, cultural participation, helping others. Mars colonists have clear purpose initially: build the colony, survive, enable future growth. But after decades, when the colony is established and routine, what gives life meaning when you're maintaining life support systems and growing food in underground farms, knowing you'll never return to Earth, never see forests or oceans, and your children will face the same limited existence? Some might find meaning in the historic nature of colonization, being pioneers, expanding human presence. But pioneers on Earth eventually saw their settlements grow into thriving communities with opportunities exceeding their homelands. Mars colonies, constrained by resources and physics, might never offer such hope. Your descendants face the same limitations you do forever. Suicide risk is elevated in isolated populations. Antarctic research stations have higher suicide rates than general population. Submarine crews undergo psychological screening to exclude high-risk individuals. A Mars colony would need similar screening, But you can't screen out all risk. Chronic stress, confinement, lack of purpose, relationship problems all increase suicide ideation. A colony can't afford to lose people to suicide, but preventing it requires mental health resources that small populations struggle to provide. Mental illness generally is problematic. Schizophrenia, bipolar disorder, major depression all have onset typically in late teens or 20s. A Mars colony might screen colonists to exclude known mental health issues, but screening doesn't catch everyone. Disorders can develop after arrival, stress can trigger latent conditions, and screening out everyone with any risk factor eliminates much of the potential colony population. Treating mental illness on Mars is challenging. Psychiatric medications require pharmaceutical industry to manufacture. Psychotherapy requires trained psychiatrists or psychologists, specialists your small colony might not have. Hospitalization for acute psychiatric crises requires secure facilities and trained staff. None of this scales to small populations. The permanence of the commitment is psychologically crushing for some people. When you go to Mars, you probably never return. Launch windows occur every 26 months. Launch costs are enormous and seats are limited. You're making a permanent decision to leave Earth forever. Second thoughts, homesickness, regret, none matter. You're trapped by physics. Historical analogies are imperfect but instructive. Prisoners in solitary confinement experience severe psychological damage within weeks. Explorers trapped in Arctic ice endured extreme psychological stress. Some expeditions descended into madness and mutiny. Colonists on remote islands sometimes gave up and abandoned settlements despite huge investments. All these situations had escape as possibility, even if difficult. Mars colonists have no escape. Group dynamics research shows that high-performing teams maintain cohesion through shared purpose, clear roles, regular breaks, and rotation of members. Mars colonies can't offer rotation. People are stuck together indefinitely. Shared purpose might fade over time. Roles might become monotonous. There are no breaks from the environment or from each other. Conflict resolution becomes critical. On Earth, legal systems and social services handle disputes. Police, courts, social workers all intervene when conflicts escalate. A Mars colony of 10,000 needs governance structures, but these must be created from scratch with limited precedent. What's the justice system? Who enforces laws? How do you handle serious crimes when you can't imprison people long-term, resource-intensive, and can't exile them? Death sentence. A murder in a Mars colony creates nightmare scenarios. You must confine the murderer somehow, but building prisons requires resources. Executing them is morally complex and removes genetic diversity. Allowing them freedom endangers others. There are no good solutions. Interpersonal violence generally is elevated under stress and confinement. Domestic violence, assault, sexual harassment, all would likely be more common on Mars than Earth. Preventing and addressing violence requires social services, law enforcement, and cultural norms that small colonies struggle to develop and maintain. The psychological cage isn't about physical barriers, it's about the impossibility of escape, the monotony of confinement, the limitations of social and cultural life, and the absence of the diverse, natural environments humans evolved in. We're psychologically adapted to Earth as much as biologically adapted, and removing Earth's psychological supports might cause deterioration that makes long-term space habitation untenable, regardless of technological solutions to physical challenges. Chapter 10. Eternal Home. We've examined every barrier to leaving Earth: gravity's energy demands, the rocket equation's exponential tyranny, civilization-scale energy requirements, lethal radiation, incomprehensible distances, impossible resource logistics, biological fragility, infrastructure complexity, and psychological constraints. Each alone creates severe challenges. Together, they form an interconnected web of limitations, that may permanently confine humanity to Earth. This isn't defeatism, it's realism. Space exploration is possible. Small scientific outposts on Moon and Mars are achievable, like Antarctic research stations, but more expensive and difficult. We can send robotic probes throughout the solar system and beyond. We might even send small crews on brief Mars visits, though the cost and risk are enormous. But large-scale colonization, cities on Mars, habitats on asteroids, generation ships to other stars, human civilization spreading beyond Earth, these may be impossible. Not impossible with current technology, implying future technology solves the problems. Impossible fundamentally, constrained by physics, biology, and economics in ways technology cannot overcome. Consider the compounding nature of these barriers. To solve radiation, you need massive shielding, requiring resource extraction, requiring infrastructure, requiring energy, requiring launch capacity, requiring economic viability, requiring populations large enough to sustain specialized knowledge, requiring biological viability across generations, requiring psychological health in confinement. Each requirement depends on others, creating circular dependencies with no clear starting point. The rocket equation multiplies all other problems. Every kilogram of shielding, every ton of infrastructure, every person, every resource must be launched at enormous energy cost. This cost doesn't decrease with better technology, it's fundamental physics. Newer rockets might be more efficient, but efficiency gains are marginal. Chemical rockets are already near theoretical limits. Nuclear propulsion helps modestly. Fusion would help more if it existed, but none eliminate the exponential mass ratios for high delta V missions. Energy requirements exceed human civilization's production capacity for any colony scale that matters. Launching millions of tons to Mars, providing power for self-sufficient colonies, accelerating generation ships to even 1% light speed, all require energy orders of magnitude beyond current production. Just build more power plants ignores that those plants require resources, uranium, rare earths, construction materials, that are themselves limited, and that increased energy production causes environmental impacts, potentially rendering Earth uninhabitable, defeating the purpose of colonization. The biological unknowns might be showstoppers regardless of engineering. If human reproduction fails in reduced gravity or high radiation, colonies die in one generation. We won't know until trying, and trying risks creating populations doomed to suffer genetic degradation and eventual extinction. This creates ethical nightmares. Is it moral to establish colonies that might doom children to such fates? Distance imposes fundamental isolation. Mars is relatively close, but still far enough that help from Earth arrives years late, if at all. Self-sufficiency is mandatory, but achieving it requires infrastructure beyond realistic capability. More distant destinations, outer solar system, interstellar, face isolation measured in decades or centuries, making colonies effectively separate civilizations that cannot meaningfully interact with Earth. Some argue technology always advances. What seems impossible now might become routine in centuries, but this argument ignores that some limits are fundamental. You cannot engineer around thermodynamics, cannot violate conservation of energy, cannot exceed light speed, cannot eliminate the rocket equation. These aren't engineering challenges, they're physical laws as absolute as gravity. Historical comparisons to past impossible achievements that later became possible don't apply. Heavier-than-air flight seemed impossible until understanding aerodynamics made it achievable. But space colonization isn't limited by lack of understanding. It's limited by physics we understand very well. The barriers aren't "we don't know how," they're "we know how," and the requirements exceed available resources by orders of magnitude. Ocean exploration provides better analogy. Humans live on land, visit oceans briefly with technology, establish temporary underwater stations for research. But we don't colonize ocean floors. Cities underwater are technically possible but economically absurd. Construction costs exceed benefits. environment is hostile, and land offers vastly better living conditions. Space is similar. We can visit with technology, establish temporary research outposts, but permanent colonization faces costs exceeding benefits while Earth remains habitable. Earth won't remain habitable is common counter-argument. Asteroid impacts, nuclear war, climate change, pandemics all threaten Earth's habitability. Shouldn't we establish backup colonies for species survival? But this logic fails analysis. Colonies dependent on Earth for critical supplies die when Earth dies. Colonies truly independent require infrastructure and resources we cannot afford to transport. And threats to Earth's habitability, while real, are generally more solvable than achieving self-sufficient space colonies. Climate change is serious but doesn't render Earth uninhabitable. It causes sea level rise, changed weather patterns, species extinctions, economic disruption. Even worst-case scenarios leave Earth more habitable than Mars. Terraforming Mars to make it Earth-like would take millennia and require more resources than mitigating climate change on Earth. It's vastly easier to prevent Earth's climate deterioration than to create Earth-like conditions on Mars. Asteroid impact risk is real but rare. Extinction-level impacts occur every 100 million years on average. We can detect and potentially deflect threatening asteroids with technology far simpler than Mars colonization. Investing in asteroid detection and deflection provides better species protection per dollar than Mars colonies that might not survive independently. Nuclear war would be catastrophic, but probably not extinction level. Even all-out nuclear exchange would leave some habitable regions, some survivors, and functioning infrastructure. Post-nuclear Earth would still be more habitable than pristine Mars, and preventing nuclear war is surely more feasible than establishing self-sufficient Mars colonies. The philosophical question becomes, should we accept Earth as humanity's permanent home? This feels limiting to species that dreams of cosmic expansion, but limitations are part of existence. Fish evolved in oceans and cannot permanently leave water, yet fish don't consider this a tragedy. They're adapted to their environment. We evolved on Earth, adapted to its conditions, and perhaps permanent residence here isn't tragic, but simply factual. This doesn't mean abandoning space exploration. Robotic probes can explore where humans cannot go. Telescopes can observe universe's wonders. Limited human missions to nearby destinations can satisfy curiosity and advance knowledge. Space-based industries, satellite networks, orbital manufacturing, solar power collection can benefit Earth while keeping humans close to home. Perhaps the dream of cosmic colonization served important purpose even if unachievable. It inspired scientific advancement, technological development, philosophical contemplation of humanity's place in the universe. Dreams need not be achievable to be valuable. The journey toward impossible goals often yields valuable discoveries, even if the goals themselves remain unreached. Or perhaps we're simply too early. Current physics and technology make colonization impossible, but future physics might reveal new principles enabling capabilities we cannot imagine. Wormholes, warp drives, manipulation of space-time geometry, these exist as mathematical possibilities in general relativity, even if likely impossible in practice. Perhaps in centuries or millennia, deeper understanding of physics unlocks capabilities that today seem impossible. But we cannot base plans on hypothetical future physics. We must work with physics we know, and that physics suggests permanent Earth residence is likely. There's profound beauty in this limitation. Earth is not just a random rock we happen to inhabit. It's the only world in the observable universe confirmed to harbor life, the only world with forests and oceans and breathable atmosphere, the product of billions of years of geological and biological evolution, creating conditions perfect for our existence. Leaving it for sterile rocks and deadly vacuum makes no sense while Earth remains habitable. Instead of dreaming of escape, perhaps we should commit to stewardship. Earth is our home, not temporarily but permanently. This realization should inspire not despair, but responsibility. We have one world, it's precious, unique, and irreplaceable. We should care for it accordingly. This means addressing climate change seriously, preventing nuclear war, protecting biodiversity, managing resources sustainably, and ensuring technological development enhances rather than threatens habitability. It means recognizing that there is no plan B, no backup planet, no escape to Mars if we ruin Earth. The dream of cosmic expansion feels grand and inspiring, but the reality of Earth's stewardship is equally profound. We are the universe's rare conscious observers, evolved on a rare habitable world, capable of understanding our cosmic context. That's extraordinary, even if confined to one planet. Our descendants might explore the cosmos through robotic extensions, ever more sophisticated probes, perhaps even conscious AI that doesn't require life support, radiation shielding, or food. Digital minds could potentially explore universe in ways biological minds cannot. This isn't human expansion in traditional sense, but it's still exploration, still discovery, still participation in cosmic story. Or perhaps we eventually contact other civilizations also confined to their homeworlds, and we connect through electromagnetic communication across light years, sharing knowledge and culture despite never physically meeting. This too would be expansion of sorts, intellectual and cultural expansion unbound by physical travel limitations. The universe is vast, mysterious, and largely beyond our physical reach. This is simultaneously humbling and clarifying. We cannot conquer the cosmos, cannot spread across galaxies, cannot escape the gravity well that birthed us, but we can observe, understand, appreciate, and marvel at the universe from our singular vantage point on this pale blue dot. Earth is not a prison, it's a garden, a sanctuary, a home. And perhaps that's enough. Perhaps that must be enough. Because the physics, biology, and economics of space colonization suggest that for humanity, Earth is not just home, it's our only possible home forever. The hardest truth to accept isn't that space travel is difficult, it's that our entire cultural narrative about humanity's cosmic destiny might be fundamentally wrong. We've been telling ourselves stories for decades. Star Trek's Federation exploring strange new worlds, Elon Musk's vision of multiplanetary civilization, Isaac Asimov's foundation spanning galaxies. These narratives shaped how we see our future, gave us hope that Earth's problems are temporary because we'll eventually spread beyond this single world. But what if these stories were never realistic prophecies? What if they were always fantasy, beautiful and inspiring, but no more achievable than magical kingdoms or supernatural powers? Accepting this requires mourning the loss of a future we imagined, but can never inhabit. It requires reimagining human destiny on fundamentally different terms. Consider what this means for existential risk. We've been comforted by the thought that even if Earth faces catastrophe, asteroid impact, nuclear war, runaway climate change, humanity might survive elsewhere. Mars colonies would preserve our species. Generation ships would carry us to new worlds. We had a backup plan, however distant and difficult. That comfort was always illusory, but recognizing its impossibility forces confronting our true situation. We have one chance, one planet, one fragile biosphere that must last as long as we exist. This recognition should terrify us into action. Climate change isn't something we can escape by moving to Mars. It's something we must solve here because here is all we have. Nuclear arsenals aren't problems future space civilizations will transcend. They're threats we must eliminate because their use ends our only viable habitat. Biodiversity loss isn't acceptable because we can rebuild ecosystems elsewhere. It's catastrophic because Earth's evolved ecosystems are irreplaceable and essential for our survival. The permanence of Earth residence changes the ethical calculus of every major decision. Do we sacrifice environmental quality for economic growth? On a temporary Earth, we might leave, perhaps. On the only Earth we'll ever have? Absolutely not. Do we risk technological developments that might have catastrophic failure modes? With backup planets, maybe. With none, extreme caution becomes mandatory. Do we tolerate international conflicts that could escalate to nuclear war? Never, under any circumstances, because there's nowhere to evacuate billions of people. Some will find this suffocating, the idea that humanity is permanently confined, that the cosmos remains forever beyond reach, except through observation. But confinement to Earth doesn't mean confinement to primitive existence. Earth offers room for vast growth in knowledge, culture, technology, and quality of life without ever leaving the atmosphere. Consider what we haven't yet achieved on Earth: sustainable energy systems powering comfortable lifestyles for all humans, complete understanding of our own biology and consciousness, exploration of ocean depths that remain more mysterious than Mars' surface, creation of art and culture reflecting the full diversity of human experience, establishment of social systems that eliminate poverty and suffering, development of technologies that enhance rather than threaten our flourishing. These are achievable goals worth pursuing and sufficient to occupy human ambition for millennia. The universe we can observe offers endless intellectual frontier, even if not physical frontier. We've catalogued a tiny fraction of Earth's species. Millions remain undiscovered. We've explored perhaps 5% of ocean floor. We've achieved only preliminary understanding of consciousness, quantum mechanics, cosmology, complexity theory. We've created just a few centuries of serious science out of potential millennia of discovery. Intellectual exploration doesn't require leaving Earth. It requires curiosity, instruments, and dedication to understanding. Perhaps the most profound shift required is moving from expansion mindset to stewardship mindset. Expansion assumes more is always better, more territory, more resources, more growth. But unlimited expansion is impossible in finite systems, whether planetary or cosmic. Stewardship recognizes limits and asks how to thrive within them. It's not about conquering new worlds, but about maintaining the world we have. This shift challenges deep cultural assumptions. Western civilization especially embraces frontier mythology, pioneers pushing westward, explorers discovering new continents, astronauts venturing into space. These narratives celebrate expansion, discovery, conquest of new territory. But Earth has no new continents to discover, and space offers no viable colonies. The frontier closed not with California's settlement, but with recognition that physics prevents cosmic expansion. What replaces frontier mythology? Maturity, perhaps? Adolescents seek independence by leaving home. Adults recognize that some dependencies are permanent and healthy. Humanity's adolescent phase imagine leaving Earth home for cosmic independence. Adult humanity recognizes that dependence on Earth isn't weakness but reality, and that thriving within this relationship requires wisdom, not escape. This maturity enables different questions. Instead of "how do we leave Earth?" ask "how do we live well on Earth indefinitely?" Instead of "how do we terraform Mars?" ask "how do we maintain Earth's habitability?" Instead of "how do we reach other stars?" ask "how do we create sustainable civilization on our star's third planet?" These questions have answers. We know broadly what sustainable civilization requires: renewable energy, circular material flows, stable population, equitable resource distribution, protection of biodiversity, and ecosystem services. Achieving this is difficult, but not physically impossible, unlike space colonization. The barriers are political, economic, and social, not thermodynamic or biological. We can solve them if we commit to doing so. The tragedy would be destroying Earth's habitability while pursuing impossible dreams of escape. Imagine future generations inheriting a degraded planet, depleted resources, destabilized climate, collapsed ecosystems, because we spent treasure and effort on Mars colonies that never achieved self-sufficiency while neglecting Earth's maintenance. That's the real risk. Not that we remain on Earth, but that we damage Earth while dreaming of leaving it. Some will argue this perspective lacks ambition, that settling for Earth-only existence represents giving up on human potential. But this inverts reality. The ambitious goal isn't escaping Earth's constraints, it's thriving within them for as long as possible. Building sustainable civilization that could last millions of years is vastly more ambitious than establishing doomed Mars colonies that fail within generations. Consider the timescales. Space enthusiasts talk about making humanity multiplanetary within decades or centuries. But civilizations on those timescales are infants, hardly begun, barely tested by time. Earth has hosted life for 3.5 billion years, complex life for 600 million years, human civilization for 10,000 years. Creating Earth civilization that lasts another million years, expanding culture, knowledge, flourishing while maintaining planetary systems, that's truly ambitious. That's a goal worthy of human capability. We stand at a pivotal moment. Climate change, biodiversity loss, nuclear weapons, and other existential risks threaten Earth's habitability. Simultaneously, we're recognizing that space colonization won't save us. This convergence forces a choice: commit fully to Earth stewardship, or continue splitting attention between unrealistic space dreams and insufficient Earth protection, likely achieving neither. The choice seems obvious when stated clearly, yet cultural momentum towards space colonization remains strong. Billionaires invest fortunes in rocket companies. Space agencies plan Mars missions. Science fiction continues depicting cosmic human futures. These efforts aren't entirely wasted. They advance technology, inspire youth, expand knowledge, but they should be understood as exploration and science, not colonization and salvation. Accepting Earth as eternal home doesn't mean abandoning wonder or ambition. It means directing wonder toward understanding Earth's complexity and ambition toward maintaining its habitability. It means recognizing that we've already won the cosmic lottery. We exist on the one world inaccessible universe that can support us. That's not limitation, that's fortune beyond measure. The universe is vast, ancient, and indifferent to human presence. We are tiny, recent, and dependent on specific conditions found nowhere else we can reach. This is humbling, but humility is wisdom. We are not cosmic conquerors, we are Earth's children, utterly dependent on Earth's continued habitability, capable of understanding our situation, but unable to transcend it. And perhaps that's exactly as it should be. Perhaps every technological civilization faces this realization, that the universe's scale and their biology's specificity confine them to homeworlds, that dreams of cosmic expansion must give way to commitments to planetary stewardship, that maturity means accepting limits and thriving within them rather than seeking impossible escapes. If so, we're joining a pattern that might be universal. Countless civilizations throughout the cosmos, each alone on their world, each learning this same lesson, each choosing between sustainable local existence and unsustainable expansion attempts. Those that choose wisely might endure for millions of years. Those that don't likely perish, having damaged their homeworlds while dreaming of leaving them. We can choose wisely. We can accept Earth as home, commit to its stewardship, and build civilization that lasts not centuries, but millennia or longer. This is the true frontier, not space, but time, not expansion, but endurance, not conquest, but care. Earth is all we have, Earth is all we need, and if we're wise, Earth is all we'll ever want. Throughout this exploration, we've discovered why escaping Earth represents perhaps the greatest challenge humanity has ever confronted. Not because we lack ambition or ingenuity, but because reality imposes constraints that ambition and ingenuity cannot overcome. We've seen how Earth's gravity well requires tremendous energy to escape, how the rocket equation creates exponential barriers to space travel, how the energy demands of colonization exceed civilization's production capacity, how radiation threatens biology in ways we cannot adequately shield against, how distances in space isolate colonies beyond any possibility of meaningful interaction with Earth. how resource logistics makes self-sufficiency nearly impossible, how human biology evolved for Earth conditions and may fail in space environments, how infrastructure complexity exceeds small populations' ability to maintain, and how psychological stresses of confinement and isolation might break human minds before physical challenges break human bodies. But perhaps the most profound realization is that these barriers aren't separate challenges to be solved individually. They're interconnected constraints that amplify each other. Solving radiation requires mass for shielding, which multiplies launch costs through the rocket equation, which requires more energy, which demands more infrastructure, which needs more people, which requires more life support, which adds more mass, creating a vicious cycle with no clear breaking point. Every solution to one problem makes other problems harder. As you continue your life after watching this, consider what it means to be permanently bound to Earth. You live on a planet that's 4.5 billion years old, orbiting a star that's one of hundreds of billions in a galaxy that's one of trillions in the observable universe. You exist in the only confirmed habitat for life in all that vastness, a thin layer of breathable air clinging to a rocky sphere, maintained by complex systems evolved over billions of years, creating conditions so specific that even Mars, our nearest planetary neighbor, differs enough to kill you in minutes without technology. This isn't cause for despair. It's cause for wonder and responsibility. You are connected to this planet in ways deeper than geography. Your biology is tuned to Earth's gravity. Your immune system adapted to Earth's microbiome. Your psychology shaped by Earth's environments. Your very atoms cycled through Earth's ecosystems countless times. You aren't on Earth, you are Earth, temporarily arranged into a form capable of consciousness and contemplation. When you look at the night sky, you're seeing a universe largely beyond reach. Those stars are not destinations but beacons, sources of photons that traveled years or centuries to enter your eye, carrying information about cosmic processes we can study and understand but likely never visit. The universe is not ours to colonize, it's ours to observe, to comprehend, to appreciate from our singular vantage point. This recognition should fundamentally change how we treat Earth. There is no backup planet. Mars won't save us if we destroy Earth's ecosystems. The Moon won't house refugees from climate catastrophe. Generation ships won't evacuate billions to distant stars. We have one world, and it must last as long as humanity exists. This isn't a limitation to overcome, it's a reality to accept and adapt to. The great achievements of human civilization, art, literature, music, philosophy, science, architecture, all emerged on Earth, created by humans, breathing Earth's air, walking on Earth's surface, looking at Earth's sky. Our dreams of cosmic expansion emerged from this same context. Perhaps these dreams served important purposes, inspiring technological advancement, encouraging big-picture thinking, promoting international cooperation on space projects. Dreams need not be achievable to be valuable, but now we must dream different dreams. Instead of Mars colonies, dream of sustainable Earth civilization. Instead of generation ships, dream of generation stability, societies that persist for millennia by living within planetary boundaries. Instead of terraforming dead worlds, dream of maintaining our living world. These dreams are achievable and arguably more important than fantasies of cosmic escape. The technologies developed for space exploration can serve Earth. Solar panels developed for satellites power homes. Water recycling from space stations could address water scarcity. Closed-loop life support systems inform sustainable agriculture. Remote sensing satellites monitor climate, forests, oceans. Space technology's greatest contribution might not be enabling space colonization, but improving Earth stewardship. Consider future generations. Your descendants will likely live on Earth, not because they lack ambition, but because physics limits their options. What kind of Earth do you leave them? One depleted and damaged by short-sighted exploitation, or one maintained and cherished as the precious, irreplaceable home it is? These are the stakes. There is no escape route. There is only preservation or loss. The universe will continue expanding, stars will continue burning, galaxies will continue evolving, all without human presence. This doesn't diminish the universe, it simply reflects our place in it. We are local phenomena, products of one planet's particular evolutionary history, adapted to conditions found nowhere else, capable of understanding our cosmic context, but unable to transcend our biological and physical limitations. And somehow, this is enough. You don't need to colonize Mars to live a meaningful life. You don't need generation ships to create lasting value. You need only to exist consciously, to love and create and learn and connect with other conscious beings, sharing your temporary existence on this temporary yet ancient world. If you've made it this far, consider subscribing and giving this video a thumbs up. These deep examinations of physical and biological realities take enormous effort to research and create. Check out my video on what happens when the sun dies. It explores Earth's ultimate fate billions of years from now, long after humanity is gone. I think you'll find it thought-provoking. Right now, at this exact moment, you are standing on the surface of a planet traveling 30 kilometers per second around a star, which is orbiting the galactic center at 220 kilometers per second, while the galaxy itself moves through space at hundreds of kilometers per second. You are already traveling through space at tremendous velocities. You are already on a spacecraft, the only one that can sustainably support human life. Earth is not a prison, it's a sanctuary in a largely hostile universe, a rare exception to cosmic sterility, a garden in a desert stretching billions of light years. You were born here, you will die here, and your descendants will live here for as long as humanity endures. This is not a limitation. This is home.